Okay. Alright, welcome to another video. I'm coding. Doing more coding, so yeah. You can see I have a large file here. Wait a second, guys. Okay. So I have a large file here because last time in the last video I was working on doing the Turing machines, like enumerating all of them. I'm trying to implement this thing. Where is it? It's here somewhere. Somewhere it's here. Come on. Come on. I think it's close. Yeah. Okay. It's here. Yeah. Where are the tables? Where are the tables? Here we go. Okay. So, yeah, I was looking to reproduce this table, and I kind of gotten pretty close. It's still not correct, or like my numbers still aren't the same as what they got in the paper, but it's pretty close. Um, it's pretty close. It's off by like a bit, just a little bit. So they say 0 is 0.25. My 0 was 0.27 almost, and 0 is 0. I got 0.09 and they got 0.1. So I think my implementation for the Turing machine it could be slightly off, not gonna lie, could be slightly off, but that's okay. We keep going, because I don't think I'm too lazy to actually do this, I guess. I don't know. Let me check. Okay, this would only be a problem if, let's see, if we didn't have the same number of strings. Yeah, what is this? So what do they say? 128-bit strings? So that would be like the maximum. 1, 2, 3, 4, 5, 6, 7. 2 to the 7 is 128. That is true. Okay. So yeah, I just want to make sure that I have all the same strings that they have. Let's see. So let's just count. There's 3 of these things, and how many do they have here? They have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 41, 42, 43. So 3 times 43 minus 1 is 128. Wait. That's what they said. It was 112. Okay. Well, I knew that. I knew that. Definitely knew that. Alright. So what I'm gonna do is take a look at these strings. And here I'm just gonna do this again for the 3-state Turing machines and see what I get. I'm gonna include the frequency 0 Strings. Okay, there's quite a few of them. Quite a few of them. I think that's because we checked. None of these even have frequency. Okay, some of these don't have. So this one doesn't have any. So how is that? So 3 1s and 3 zeros is not a thing. Let's find that somewhere. Maybe they don't have it. Let's see. Oh, they do have it. But this is from D4. Is there another one? No. This is from D4. I calculated D3. Okay, I don't think that string appeared for D3. So that's good news. That is good news. Alright, so I didn't get that one. I didn't get this one or this one. So what is this? 110100. Yes. Yes. So that is from D4. It is not in D3. This is good evidence for us that we coded this correctly. Okay, this is in D3. Oh. Whoa. This. Okay. Damn, I think we did. So this is actually in D3. And it's not 0. But it is a very small number. It's probably just one Turing machine that produces it. That's what I'm thinking. Maybe. I don't really know. Don't really know. It's probably not one. Maybe it's like 2 of them or 4 of them. Some multiple of 2. Cause yeah, there's kind of a pattern here. There's always multiples of 2. Yeah, there's a bunch. There's a bunch here that we didn't get. Do we have okay, this yeah. We definitely messed up. So this string definitely appears. This appears. We have all these strings that is not appearing in the thing. I mean, this one is there. This one is there. But you know, what about all these strings? Okay, what about this one? Is this in there? Yes, it is. Okay, this is not right. This is not right. Not right at all. Okay, what I want to do is add up all the strings that have a non-zero frequency. And yeah, I want to print that out just to see how many strings have frequencies greater than 0. That's pretty verbose. Strings greater than 0 frequency. Couldn't get simpler than that. Alright. Oops. How is that pasting in such a weird way? Alright. Okay, let's go back. Let's build. Let's build it. Let's do that. Okay. 95. Okay. So I'm missing 33 strings. And that is probably something right there. That's probably something. I don't know. Okay. So we're on a journey, okay? We are trying. So the problem here is I want to debug this and see. Also, there's some length 7 strings that I have, which, yeah, those are good. Let's put that. Okay. So the problem here is now I need to figure out why they are not being included. Why is their frequency 0 when it should be greater than 0, apparently, according to the paper? And yeah, that's problemo. Alright, so let's see here. Let's take that out. And let's redo this. Let's only include the strings that had 0 frequency. Also, let me just put this real quick. Let me move this here. Oh my god. Let me move that so it's actually correct. Let me move that so it's actually correct. Okay. Alrighty, so there's quite a few of them. Most of the strings for... Wow, what is this? Is this length 8? Length 9? So let's change max string size so it doesn't go up too much. Let's put 8 to be the limit so we don't... Yeah, so we don't get too many. We don't get strings that we know can't be produced, because the 3-state Turing machines apparently don't produce 7 lengths, any length 7, or I mean length 8 things. Okay, so let's look at this. So here's problemo. So we do get, okay, we're missing some length 6 strings, a lot of them. And that's kind of weird. Let's do some numbering. So let's count. I want to count how many are missing from each length, so we can maybe do some mathematization. Yeah, so I'll put right here zeros within the length is going to be that. And then here we're going to say plus plus. And then here we're going to print the how many you know, how many. Alright. This will help. This will give us more information. Alright. Actually, let's not put within the length. Let's actually put the length. Zeros in length. And let's put string length. Whoops. Okay. Okay. That's good. That is good. So, alright. Ooh, look at that. 120. Whoa, what? Wait, 7? How? What? 121? I think it kept. That doesn't seem right. Did I do something wrong? Did I do something wrong? So this is 38 of them. Yeah, okay. How many strings was I supposed to? What? Isn't it only 128 strings? And how is it that I have 121 zeros in length set? Is that even correct? I don't think that's correct. That can't be right. Right? It can't be right. Does this look like 121 numbers? I don't think so. I don't think so. Oh, it is. What? What? Alright, I'm just confused now. I'm confused. Oh, cause some of the okay. Yeah, okay. The number of length 7 strings, it's only these. Okay. Yeah. Yeah. Oh, there's some here too. God damn. Alright, I think I'm gonna have to copy this or I don't know. Do something with this. Cause where are all the length 7 strings? Like this is one of them, I think. No, that's 6. Alright, 1, 2, 3, 1, 2, 3. 1, 2, 3. Wait, this is 7. These are 7. And these are 7. Right? Yeah, these two are 7. These look pretty cool. Alternating thingy. Is there like... So how many did we get? I think that's a better number to keep track of. So it's not like the zeros within the length. Let's do not zeros in the length. How about that? Okay. Wait, I think I already added that. Well, this is in total. This we still increment this, but yeah. Yeah. I'm gonna do this. I'm gonna do this. Alright. I think this is gonna be better, easier to check thing. Alright. So we have 7 strings that are not 0 in length 7. So let's look at length 7. Let's actually let's change this as well. Put this here just for funsies. So if it's greater than 0, do This else is probably going to be 0. Or negative, actually. So, I'll just put here frequency. Okay. So let's do that. Let's do that. Okay. Okay. So we have 7 length 7 strings. So let's keep. Wait a minute. I think it's the length 6 strings that are failing. Because there's 38 of them, right? And we have 95 when we should have 128. And there's 33 that we're missing. And here we have 38 zeros. Yeah, all of these have strings. Okay. Yeah. So 33 of them are missing. Here we have 38 zeros. Here we have 121 zeros. So I'm not sure which ones they are, but let me check. Let me check again. So let me count how many length 7 strings they got. If they got 7 of them, I might have to check. I might have to do some number calculations. Alright. So, okay. So we have here 1, 2, 3, 4, 5, 6, 7. What? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14. I think it's just 14 of them. 14? Huh. That's odd. 14 is 2 times 7. Let's try something. That's weird. That is weird. So what if we did 14 plus 26? Well, actually, no. So we have 7. Alright, let's look at something. Let's look at the exact strings that we have. Okay. That one is there. What about this one? So this one has a frequency of 8 in our thing. Which is 2 times greater than the frequency of this one, which was 4, apparently. So let's just multiply 4.663 times 2, which we did get to be approximately the same as this. So I think we got the frequency of these relatively correct. These two should do that. But one thing I'm not understanding. So we're missing some of the length 7 strings. Yeah, we're just missing some of them. There's 121 of them that are missing. Yeah. That's just missing. They're just missing. There's 121 that are missing. So here they have 14. So we counted 14 length 7 strings, right? Got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, and all of these have the same frequency, and these two have double the frequency as of these. Let's see how that turns out. Okay, so right off the bat, I'm missing one of them. So I have this one, right? But I don't have this one. But it should be there, because I remember there's two of them that are supposed to be double the frequency, but I only have one of them that is double the frequency. And 1, 2, 3, 4, 5, 6. I have 6 of the normal ones, and here there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm missing half of these. So I think in length 7 I've only got half of them. I only found half of them. So that is quite odd. And another thing to note is that they all start with 1. So how about the ones that are missing, that I have missing, I think they start with 0. Right? So that's another thing. These all start with 1. And especially this one starts with a 0. But it's like the inverse of this one. But it starts with a 0. So maybe that's why I don't have it. Okay. Let's go back to printing all the 0 strings. And I want to see what they look like if they have a lot of zeros in the beginning. That's probably a pattern, I don't know. Well, okay, a lot of these have 1s, but I think these are just not included. Because you can see here, a lot of these have zeros. Well, the one I should be looking at is in length 6. Because, I don't know. Do these have... How many length 6 strings do they have? Well, I can calculate that. I know they have 14 length 7 strings, right? So let's go back to printing just the ones here. I should probably maybe don't even print. I should not even print those. I should maybe just do these just so I can do the math. But anyways, so there's supposed to be 14 strings in like 7. I got 7 of them. So my question is, how many am I missing in length 6? So let's do the total. Alright. So let's count all the not zeros. So we have 2 plus 4 plus 8 plus 16 plus 32 plus 14, right? And that is as many strings there are. Thingy. So there's supposed to be 52 in length 6. 52. So in length 6, okay, it's by half again. We're missing half of them. We're missing 26 of them here, and we're missing 7 of them here. So somehow them being in half, they don't get counted. Maybe my Turing machine thing is correct, but the actual the strings, I don't know, like they're not getting counted properly. Maybe when they get converted to binary, thing or whatever. I'm not sure. Maybe some strings get double counted. That could be it. That actually could be it. Alright, let's go back to printing. The not zero stringies, so we can know which ones are which. So I think what I'm gonna do is do a test, actually, and I'm gonna look for the Turing machine right here, right? And I'm gonna do this, and I'm gonna put the right there, and I'm gonna look for this string in the three state machines, and if it finds it, then you know, that's good. Oh, I didn't find it. It went to the four states. Weird. Weird, weird, weird. So the Turing machines, I guess, themselves are not doing it. What if, okay, maybe it's the array compare. I mean, that doesn't make sense. That does not make sense. So what if I do something else? Oh. So this isn't working, right? Array compare? Or the output. The output isn't working because we don't use array compare on this one. What? My God, dude. Windows. Windows, Windows, Windows. Always wanting to update. No. I mean, I probably should for security reasons, maybe. I don't really trust Microsoft. I don't really trust them that much, but that's just a personal opinion. That's just a personal gripe of mine. Alright. Yeah, so right here, I calculate I just use Turing output start. And so this is the common denominator. I think what's not working is the Turing machine itself is not working. My only problemo is how do I debug this? Because apparently I'm able to generate most of the strings, but once I reach like length 6 or 7 strings, they don't. Some of them aren't being found. Okay, I know how to test this. I know how to test it. All right, let's look for this string. All right, let's look for this string. Okay, so my theory, if my hypothesis is correct, we will have outputted this string because maybe it cut off like the first one, perhaps. So yeah, that's what I'm thinking. So maybe that's happening. I don't know. Let's do so let's do this again, and I want to look for this string. I want to see what happens. Oh, is it? Why didn't it print? Hello? That was really, really quick. is... Oh, I didn't even... Never mind. My bad. Yeah, whoops. Alright, let's go back. Checking all the thingies. Alright, so let's look at link 6. 10. Huh. We do not have it. We do not have that string. What if we have 10? What about this, where it cuts off the beginning and the end? Which is a length 5. Length 5 string. Which we do have all of them, so it's guaranteed to be in here. So let's check this out. Let's do some quick analysis here. These should be like multiples of each other, I guess. So let's just look around, see if some of these multiples are a thing. What I suspect is happening is my Turing machine thing is not executing correctly, and the Turing machine that was supposed to print out this string, you know, something happened to the output and it turned into another string. Maybe, probably a lower. Probably something got cut off. So I just want to check. Yeah, I just want to check if something happened to that string. Maybe. Let me look again for this. Maybe. No, it's not there. Okay, let's try to look for this. Maybe this is somewhere. No. So length 5 is not a thing. I mean length 6. That was length 6. Let's look at this one as well. Okay. So here are 2 of them. Right? That should have the same frequency. So let's look at those. It's these 2. Let's look for those. It's just alternating bits. Right, so 1, 0. So this one, we got 360 for that. So that's what we got, 360. Excuse me. And then this one, look at that. 32. They do not have the same frequency. Yeah, okay. This has a much greater frequency than the other one. 360 versus 32. So that's where all of the frequencies went. So let's try to figure this out. So this one got the more frequencies. The 1, 0 thing. So the alternating thingy. So probably it cut off the zeros. It weirdly cut off the zeros. So yeah, that's weird. All right, let's check this one. So this is length 5, right? Is this not a thing? Yes, it is. Look at that. It's right here. So 4 zeros and a 1. Yeah, should have the same frequency as this one here. So 4 zeros and a 1 versus 1 0 and 4 1s. So here we go. So 4 zeros and a 1. we got 192. Seems kind of high. Let's do the ones and a 0. And this one is much higher. This one is much higher. So where is this? Oh wait, no, it's supposed to start with 0. And then have the ones. This one. So this one is 236. What is it again? So 0s and a 1. The 0s and a 1. So the one that has the higher frequency is this one, apparently, which is kind of weird. Which would come from this string. And I don't know if we have that one. Let's check. In like 7. I think that's the one of the strings that disappeared. No, it's right here. But anyways, let's go check the frequency on that. We probably got that right. The frequency is the same as these other ones. But why does this have a higher... this has a higher frequency. Okay. This is looking out... This is kind of weird. This is kind of weird. Let me look at this again. So we got 0s and a 1. 0, 0, 0, 1, 0, 1, 1, 1, 1. In length 5. So they both start with 0. So this one has 236. And the other one has 192. Let's take a look at that. 192 minus 236. So this one maybe has 44 more than it should. Assuming this is the correct amount, which I'm not really too sure. Let's see if there's another thing that has the same frequency. I don't think there is. Oh, no, we got this one. 1, 0, 0, 0. 192, yeah. Yeah, okay, so that one, this one got more. This one got more, so that's a good thing to search. So this one definitely got more. Oh, maybe it came from the 6, length 6. Huh, so it cut off the 1. It cut off the 1, alright, that's odd. Odd. It cut off the 1. Do we have this in the 6, length 6? We have to, like, verify our findings. I don't think we... Oh, we do have it. Yeah, it's right here. What? Maybe does it have the correct frequency, though? It's supposed to have the same frequency as 1, 0, 0, 0. 1 in many zeros. Which does not appear. 1 in many zeros is one of the strings that does not appear. It should be right in between these two numbers. But it's not there. It's missing. Where has it gone? Where has it gone? Alright, do we have another string we can look at? So the 0001. So this should have the same frequency. Oh, that one's gone too. That is weird how they disappeared like that. Alright, let's look for something else, I guess. So I checked that one. I checked one. Wait, did I check that one? So I got this one, and one full zeros was missing. All ones and a 0. Let's look for that. So that's here, and that's 24. So that's here. So this one is here. This one which one is not here? This one is not here. This one is here. This one is here. And they have the supposedly correct frequency. So what happened to this one? What happened to this one? Did this one bleed into the 5 string or the 4 string? Oh my goodness. All right. What I think what I have to do is okay, I think I have to look just very closely at my Turing machine code, because this is probably wrong. There's something probably happening here. I kind of just wrote this quickly and I didn't actually closely look at it. I just kind of went as quick as I could. But maybe, okay, so maybe Turing reset, you know, is weird. I don't know, maybe not. Maybe not. I kind of am guessing something in here, something having to do with maybe this, like it halts before it has time to update the tape thing here. So I'm gonna try to, maybe I should comment this out. Not to, it would never halt actually if I did that. So let's bring this back. Yeah, we do have to check if it's halting eventually. So with that in mind, let's try to do this again and see what gets generated. I want to see. Oh my god, look at that. Now we got the strings. Hold up. Hold up. We have more than 128 strings. Is that... yeah, look at this. The length 1 strings are gone. I knew that would happen. Come on. Come on, that happened last time. It happened last time. Alright, let's go take a look anyways at the length 2 strings. So these are all supposed to be the same for length 2, but that is not the case for these. Right here we got a difference. Excuse me. The differences we got is, I'm guessing what happened is the length 1 strings never had a chance to happen, I guess, and I'm not sure. I'm not sure what to do with this information. Oh my god, sorry guys. So the deal with this is I got my strings. Right, I got my strings. I got length 6, which apparently missing one of them. I don't know if that's supposed to be there, but I don't know actually. I think we're supposed to have them. That's weird. Weird. I think we're supposed to have 52 in here. Yeah, I think we're supposed to have 50. So we were probably closer to the correct behavior without putting this in the beginning. So the halting state when are we supposed to check if it halts? You know, like when are we supposed to check? When do we return true? Like if it halts, you know? Are we supposed to do this after the right here? Are we supposed to do it right here? Because I'm not sure. Because doing this gives us the strings we need. But that it doesn't work. So yeah. Alright, so this is what I'm gonna do. I'm gonna put this here. I'm gonna try it here. And I'm just gonna try it in all those different locations and then see which maybe certain combination of those would result in this working properly. So look, now we lost half of these and half of these, but at least we have hopefully we have the length 1 strings, and we have these kind of it's slightly this one is slightly different. This is weird. Okay, so okay, something fishy is happening. All right, let's look at the length 3. Let's look at length 3. So 0, 0, 0, 1, 1, 1 should be the same, which they are not. Okay, okay, something is happening. This one is greater than this one. This one has the greatest frequency among all of them, length 3 strings. This one has less. So my hypothesis is that it bled into this one. Okay, this is kind of weird because they have different amount. I mean, are these approximations? Are these exact? I think these are. I don't know. I don't know. I don't really know. Okay, because they got 0.101. Let's convert that into a fraction. It's 1 over 1 over 1,000. I don't know. I don't know. Alright, let's do that thing where I was thinking where I was going to check how many exact thingies we're supposed to have. So 15 million. So I'm going to get this number, and what they did is they divided how many by this, and they got this. So if I multiply this by this, we should get the number. So let's check that number. So 150,590,72 times 0.101, and I got a decimal. Okay, but yeah, I got a decimal. What's odd? Okay. Something is weird here. Something is weird. Because here I put total strings. Is that much? Maybe it's because of the output length I put. So how many? Because like how many Turing machines am I? If I'm getting this correct, this should be. I should get this number. If I did all the Turing machine thingies correctly. So let me go back here and try to get that number out of my code. So Yeah, total strings that I'm considering is, oh, hold the phone, guys. Am I just calculating this incorrectly? How am I calculating this? Total, guys, wait. No, this is correct. This is correct, right? If it halts, then we add 1 to the total strings. And strings greater than max. What? So what did I get? 0 strings greater than max, and then I got this. What? What is happening here? Am I just not checking all the Turing machines? Maybe I'm missing some of them, because this number is definitely smaller. I guess, what is it, 7 million something? This is 15 million. Wait, guys. Wait a minute. The number they got divided by 2 is this number. So I'm literally just going over half the strings. That's why some of the frequencies are... okay, that's why in like 7 I'm missing like half of them, and here I'm missing half of them as well. Oh my god. Okay, so what is happening? What is actually happening? Is it this? I'm not even enumerating all of them, apparently. What is going on here? What is going on here? Total. So maybe the ones that halt? How is it possible that the ones that halt... No, this is just weird. This is weird. So... what am I supposed... So 0, 1, 2, 3. Is this number too small? Should I increase it? Let's do 50. Let's just try that out. It's gonna take a little longer, but I just need to make sure this is correct. Okay. No, we still running half of them. Something is fishy. Something is definitely fishy here. I even increased the Busy Beaver steps. What is this? Is it because of this? 10? Does it go to 10? Is that what's happening? I do T number of states minus 1. T number of states minus 1. Is that just bad? Is that just wrong to do? I don't really know. So here I put max states 3. Right? And then I do change state, right, to 3. And then I do n plus 1 for number of states. Okay, so that happens. And then here it does number of states minus 1, so back to 3. So 0, 1, 2, 3. I don't know, but let's put 50 here just to make sure, see what happens. Maybe it'll I don't really know. Maybe it'll actually take long. Wait, did it take longer? So 12.4 seconds for that one. Yeah, it kind of did take longer. So maybe that was here. Okay, it took even longer. But still, it only went through half the strings. Oh my goodness. All right, we got a little bit of a thing going on here. We got a little bit of a thing going on here. Let's do this so to be quicker. I don't need to know this information. So what is not working? We are only traversing half the... We're only discovering half of the halting machines. Okay, this is so weird. Is that true what they're saying? Guys, where do they even get that number from? Look at this. Look at this. Number of end state turn machines which halt. We got the same number. We got literally the same number. What are these people talking about? What are these people talking about? Oh my god, what? Jesus Christ moly. Alright. So did we actually get the correct... So what is the difference between our code and their code? Did they use a different halting thing, or what Turing machine are they using? Because they got 2 times as many Turing machines. When it even says on this website that it's not even that. So is my thing correct and their thing isn't correct? Which that would be kind of weird. What are they saying here? There are this many machines that halt. What? I thought... Am I supposed to get all of the Turing machines? Even the ones that don't halt? Is that what they do? This is just weird because this isn't even correct. This isn't even correct. Oh my god. Alright. Alright. Let's just... Okay, so here is the number of, you know, halting Turing machines. So this is 16 million halting or not Turing machines. So this is the 1, 2, 3. I think it's this. This has to be the 3 state. And they got this number for weirdly whatever, and they say there are this many machines that halt. So are they considering less machines? Because actually there's this many that halt. Yeah, yeah. There's some stuff here. There's some stuff here. I don't know what this means. Halt free. Yeah, I don't know. Here's the prime numbers, apparently. Why would they... This has no relation to Turing. I mean, it does, technically, but whatever. Alright, I'm gonna have to read this. And, okay. Let's keep reading this. Right here. Did I just do this wrong? Is this the number? Or is this the number that we're looking for? It just can't be. I mean, we're doing this, which is 2 times less. So that it's conveniently 2 times less. But anyways, they did get this correct. Which this is 1. They said there's 32. Never mind. What? They said there's 24 that halt. They said there's 24 that halt. But there's actually 32 of them that halt. And the next one is 9,700. Okay, they're definitely... I don't know what's happening here. $20,000. They're saying there's 20,000. There's not 20,000. There's 20,736. What? Is this... What? This is not correct. Is this correct? I don't understand. I do not understand. Maybe they do like a reduced. Oh my god, maybe they do a reduced amount. That's crazy. And they say they used 77 gigabytes for the output. Did they output like every single thing? That's okay. Alright, let's do a little test again. Let's go back to sanity check and let's run the one state Turing machines, which we end up with nothing. We end up with nothing on there, so that's not good. That means we have to go back and change our excuse me. We have to change our something here. We gotta change something. Alright, we gotta change something. Oh wait, no. We didn't, never mind. Hold up. I just didn't print them. My bad. My bad. Let's go back real quick. Let's go back to the one. Yeah. So this is okay. Alright, that's okay. This, let's look closely again. So for D2, these two are supposed to be the same. These 4 are supposed to be the same, which they are not, actually. These 2 are, you know, this one is most likely this, you know, whatever. And these 2 are the same, though, for length 1. And these 2, these are different. These are kinda different. Let's count how many length 3 strings they got. So they got 1, 2, 3, 4, 5, 6, 7, 8 length 3 strings, and I got 7 of them, which means I'm missing one of them, apparently. but I'm only considering 9,784 of them. They are somehow considering less machines than I am, but getting a different result. And kind of weirdly, they're saying that there's 20,000 of them, but there's actually not 20,000. There's 20,736 of them. So that's, I don't know what that is. I'm just gonna ignore that. And anyways, so here they got a fraction of, you know, let's do 20,000, right? Let's do their number, 20,000 times 0.328. The frequency on this one is 6560 for these two. 6560. 6560. I don't know about that. 6560. I did not get that. I did not get that. 6560. I got half of that. Precisely half. Did I get precisely half? No, I got slightly more than half. Actually. So weird. Okay, that's just weird. Is there another place I can get this information? Because I'm not quite sure my Turing machine implementation is wrong, which is, I think that's very likely. But it's either that my implementation is wrong or this is wrong in how I understand they implemented it, apparently. Yeah. Let me read a little. This number. Ah, they fill it with zeros and ones. Why did they do that? Come on. So they did. That's why there's half of them. They fill it with zeros and ones. Come on. Why did they do that? So that's the only. Is that the only difference? Oh my god. Started with the tape filled with zeros and ones. So do they mean by like 0 and 1 alternating? Or they did like a bunch of random zeros and ones? Or what did they do? That, that's just weird, because why would you fill it with ones? Because that doesn't work anymore for me. I don't know how they determine if it halts by using all ones. I'm guessing they found a way to do that, which is cool, actually, which is pretty cool. Yeah. So I think I have to look at this. Alright. I need to see what they did, though. I need to see what they did. Okay. Where did they do this? Where did they do this? So here, Yeah, so we did that same thing. Okay. Okay, so here's what they do. They say it here. The blank symbol is one of the two symbols in the first run, while the other is used in the second run in order to avoid any symmetries due to the choice of a single blank symbol. In other words, we run each machine twice. One with 0 as the blank symbol, and an additional run with 1 as the blank symbol. So I'm supposed to run it twice. Okay. That is interesting. That is interesting. So I think I have to account for that now. Or just simply write code that will well, let me look at the right here real quick. Here's what I'm gonna do. Okay. I'm gonna put this here. I'm gonna put this here as well. So what I did is I halted here. Maybe I should be halting here. I'm not sure. I don't know, but let's run it, see what we get for that. So the length 1 strings are a thing. So what if I do this? So we halt after we do the tape, and that removes the length 1 strings. So probably we need to halt before we do the output, handle the output, because then we won't have the length 1 strings. Right. So on D2, it says we have 17 strings. And I think we're missing some of them, to be honest, because we have 2 plus 4 plus 7 plus 4, which is 17. And here I think they have 18, not too sure. So we have 2 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Times 2 is 22. So they got 22. Yeah, 22-bit. 22-bit strings. They got 22 of them. So what's the difference? We got 17 minus 22. You know, whatever. We're just supposed to... Okay. So this Turing machine implementation, I think, is right. The only difference now is that we have to run... We have to enumerate all of them on a tape of 0s, but also a tape of 1s. So that is going to be here. Probably, right? It's going to be here. So we do this. And what do we got to do? I think all we have to do is Turing reset. And right here we set it to all 0s. Here I could do it so, you know, like we test it with the 0s and then we test it with the 1s. And then, yeah, we just do that. So, okay. Okay, okay, we could do that. We could definitely do that. So, let me call. So we got turn reset, and let's call turn tape 0. Let's call that what that is. So that means we do zeros, and then we're gonna do the same thing but for ones. Ones. Okay. So naturally, we do the zeros to begin it. The tape by default, but I could do the ones if I want to. So yeah, I just have to call turn tape ones after right after turn reset. So I think I have to make a second function. Maybe I could put a boolean here. Alright, I could say use ones tape, right? And I'll say here if use ones tapes equals true, then we're gonna call turn tape ones, and that will fill the tape with ones, and everything else will happen exactly how it normally happens. Difference. The difference here is we don't want to load the next machine. We want to run the same machine twice, but with one with zeros, the other one with not zeros. So we can't just do that. I think I have to make a separate function for this. That's annoying because I just had assumed that we're gonna run it with zeros every time. But I guess if we're not gonna run it with zeros all the time, that changes things. So maybe I have to change things up on this function. Yeah, I think I have to change it up. Okay. Okay. So where do we do this? Here we load. We load, run, halt, or busy for next machine. I'm gonna call this. I don't know what to do, guys. I don't know what to do. Why? I want to know though. Why did they do it with zeros and ones? Is that like a theoretical? They said it was because like asymmetric. Something with like the halting. Yeah. Yeah. So that's interesting. That is interesting. Okay. I'm just trying to figure out what to do with the code. because in the code, you know, I just got stuff to do, because like this code only works for 2 symbols. It only assumes 2 symbols. I mean, it assumes 2 symbols among other things, right? And they're right here, they're saying that they did it with zeros and ones because the 0 is like the blank and then 1 is like not blank, and then you can reverse that and to get rid of all the asymmetries or whatever. And that is true, you know, but will I ever in the future want to make this work with 3 symbols or any n number of symbols and make an algorithm for that? So if I wanted to do that, I would have to mess up some of this code. I'd have to mess it up and probably have a right here for number of symbols variable. So maybe I could do that today. I don't know. No. Today I don't want to do that. I might end up doing it. I don't know. I might end up doing it. Okay, what I do want to do though, at least, is just make sure I can generate the same frequencies that they got in their table. And I know for a fact right now I have to at least run the Turing machines twice. One with zeros, one with ones, and then check the frequencies of that. So I think I have to do something here where I'm gonna like copy this. Yeah, I gotta copy this. I'm gonna do something. I want to turn this into, put this in here. Alright, and call it something. I don't know what to call it yet, but yeah, it will do something. The reason I'm doing this, well, let me read it real quick. So this should be called something like, okay, so what does it do? Update frequency, or like, yeah, this is probably, yeah, that's what that does. Use the current Turing output and updates. Oh, let's say this. Add output to frequency table. That's a better thing. Add output to frequency table. Or I could say mark output in increment output string in frequency table. Yeah. There we go. Alright. Update thingy. Alright, whatever. So we increment output string in frequency table. Okay, so this probably has to change, and I'm probably gonna have to make another variable or something. So what I'm gonna do is basically just make a copy of this. Yeah, this is gonna get pretty messy. So I'm going to call this ones and zeros. I'm going to call this zeros tape. It's going to be called ones and zeros tape. So there's going to be 2 of them. And to do that, I'm going to do this. And then I'm just going to do it again. Basically, just do it again. But here I'll say turning tape ones. And just for completeness, I guess here I'll put turning tape zeros, even though I don't need to do that. It's already in turning reset. What that does. So yeah. I will make 2 more variables, run halted zeros and ones. Okay, simple as a pimple. Simple as a pimple. Alright. Simple as a pimple. Alright, so this is running it twice and updating accordingly, and then it returns the next one. So this one, this is the one I want to use. Here I'll put the zeros tape. Let's see. This isn't accurate all the way. This isn't all the way accurate. Oh my god. This isn't all the way accurate, my friends. This is not all the way accurate. I can't just do that. Because I have to actually store the output. Store the output. For this. Yeah, I gotta store the output. So here I'll put the ones output number and the zeros output number. How about that? And then if it did halt, right, I will put the output for the in number form here. And okay, so let's do that. Let's do that. I don't know where how did I do that? I did it here. Convert binary array to number. Is that what I'm doing? Is that what I'm doing? I think that is what I'm doing. Okay. So this thing, I'm gonna move this back a little bit. There's an ant on my desk. We got it. Alright. So right back here, I'll do this. I'll say convert binary array to number. Yeah. No, this should probably be further up, closer to the Turing machine stuff, probably here. And I'll make a thing here. Int convert Turing output to num. Yeah, and that is gonna be a thing. So I'm gonna say convert binary array to num, and I'll say this, and I'll say this. So easy peasy lemon squeezy. we convert turning output to a number. Easy. Let's check if that works. Right. So let's check if that works. So we can do this. We're gonna say num value equals convert turning output to number. Lovely. And if this works, doesn't, okay. What happened here? What happened? What? Oh, whoops. Yeah, because this was defined after. So I have to put this here, just so it will compile. Here, there's a thing somewhere at 377. And I'm gonna do that. And this does okay. Okay, there's problems. There are problems. Oh my goodness. So here, at 401, I used this when it probably should have been this. Even though I don't even use, probably don't even use that anymore. 532, there's another one. Let's do the zeros here. Let's do, okay. Okay. So this still works. Kind of. I think it still works. So we're good to use the convert this thing. The reason I'm lost now, I forgot what I was doing. No, I remember now. I remember. This one. So right here, the ones output number is, we're going to convert the output to a number. Yes. And then here we're going to do the same, but the zeros output number is going to be that. Right? And then we get the next thing. Okay, so here we're going to go in here, and then we're going to say ones and zeros. Boomity boom. What does this do? What if we just put in num value in here? We would not use. So we gotta keep the length and thing. Okay, so we gotta do this. We gotta input the length and the value. So I need to keep track of the length as well. So not just the number, but the length as well. Alright, so let's do that, and let's do that here. This is straightforward. So the length equals that, right? And right here, we get that, hold the phone, what did I just do? I switched them. This is the zeros. Whoops. Oh my god, rookie mistake. Rookie mistake, alright. Is this correct? So we do ones, length, size, output, ones, number, size, zeros. Okay, that is much better. We do turn reset. Load machine, perfect. Alright, let's go back here. I think I also have to keep track of halted if they halted. So there's another. Oh yeah, I did. I put that here. So, my God, freaking. Run halted, zeros, ones. All right. So here we go. Let's do this. So if run halted ones, we do that. Else, if run halted zeros, we're gonna not else if it. We're just gonna do this. So if it halted, right? If it halted, so if the ones halted, we are gonna do the ones output length and the ones thingy, which also this right here. I think I'm gonna call this num, just to make it a thing. So this is gonna be the ones, this is gonna be the zeros. Okay, so zeros. 1 0. So if it halted, we're adding it. If the zeros halted, we're adding it. Okay, and right here, this let's just triply make sure we do this. Huh. Halted. Is this supposed to be run halted? Because this doesn't change the thing. So we just say if run halted, and then we're gonna say run halted zeros equals to true. We gotta propagate. Right, we gotta propagate the thingy. There we go. So yeah, so this is connected now. The halting is connected. It is all good and probably all good. So yeah, doesn't this look prettier? This actually looks a lot prettier. I don't know what happened here, but this function used to be a lot more stuff in it, I think. Anyways, let's look at it and let's see what happens. Oh my goodness. It definitely changed the frequencies. I think it did not change them for the better. We actually inflated the ones by a lot more, and I think, but we are considering more of them, which is kind of weird, not gonna lie. And we do get all the strings, though. We now get all the strings. Now we get 22 of them, which is what they got. One thing though, one thing. The total strings is off. Apparently it's off. Apparently, I got a lot more halted strings. So let's just double, triple, quadruple check what is going on here. So every time we run this, we do, if it's under the thing, we put it in the string frequencies. We do count total strings every time we do this. I don't know if we're supposed to do this. I'm not really sure. So maybe we don't do this, and maybe we do like that. This seems wrong, but I'm just gonna put it anyways. It just seems wrong, but I'm gonna do it. Alright. I mean, yeah, we just This is above 1. It's not. That's not. Yeah, that's not good. Okay. So this is more than half. So I get more than half. More than half of them are these. But here they don't get more than half. They get like this number. So my question is, again, why is it still different? Why do they get only 6,088 of them? And that's not even close to that. This is just so weird. This is so weird. Oh my god. Okay, because here they say, because like on here, they get this number, right? Which is correct. It's that's 2 times this number. Alright, that's correct. Okay, for 3. But for 2 they say they get this much, which is 6,088. Which is not 2 times this. Weirdly. Weirdly. And this, they get 24. What? And this is just completely wrong, isn't it? 24, they're saying, are they saying 24 turn machines halt out of the 64? No, there are 32 of them halt. So what is actually happening here? What is actually happening? I do not know. Let's run it for 1. See what we get. And yeah, of course we get 2 times. And it even has a different frequency. Different frequency amount. This, okay, there's got to be more to it. They'd have to be doing something. Okay, I think I know what happened. Maybe the Turing machine, like if I change the symbols, right? Like if I flip the tape, maybe I also have to flip this, the right thing, right? Maybe I have to flip it. I don't really know. I do not really know. Maybe I'm supposed to treat the tape different. Maybe I'm supposed to put like right here where I write to the tape. Maybe I'm supposed to check like which one is the blank symbol, and then it'll, I don't know, it'll like flip it or something. Like run it once with the symbols and then run it twice by flipping the symbols. So maybe that's what I should have done. And yeah, I don't know. Maybe I should have done that. Who knows? Who actually knows? Alright, so let's try that out, I guess. Let's try it out. Let's do something. Let's introduce another variable. The blank symbol. Right? Let's do that. So the blank symbol will be 0 by default. Okay. And I'm also gonna put that here. Right? Blank symbol is 0. I don't really know what to put here, but I think maybe it's supposed to write the opposite, right? T dot write. So I'll say if T dot write equals blank symbol, then we're gonna write a 0. Okay, well this can't just do that. So tentry dot right, if it equals the blank symbol, right, and we're gonna write a 0 and else we're gonna write a 1, and that's what we're gonna do, and that's how you flip it. That is how you flip it. So I think I have to flip it over here. Oh my god, okay, I gotta flip it here. Right, I probably gotta do that. So I'm gonna say t blank symbol equals 1, because initially it is 0, and but yeah, it should be 1, I guess. Oh my god, it worked. It actually worked. It actually worked. Okay, wait. Is this what I had to do all along? Is this the solution I'm looking for? So if I do 2, right? Ooh. Ah. These are the same. Right? These are now the same. These are still not the same. Oh my goodness. Oh my goodness. Alright, let's do something. Let's run it for 3. And see if we get the symmetries. And I hope I do. That's all I'm saying. I hope I do. I hope I get it. This should take longer than normal. Longer than it has been taking. Oh, come on. Is it how long is this gonna take? It can't be that long. Come on. What is this? What is this? It's only supposed to be 2 times longer, which should be like around 40 seconds at maximum. What is it doing? Jesus. Oh, I was correct. Okay, my bad. I was a little impatient. Ooh. We got all the strings now. Okay. Okay. Okay, we got all the strings. All right, let's do some checks. Let's look at the. This is exciting. This is exciting. We're actually getting it. My God, we are actually getting it. Okay. So these are, they're just supposed to be the same frequencies. What is it? The ones that start with 1 are kind of the same frequency. Let's look at these two. Let's see if we got these two correctly. So this one is 14. Oh man. I don't see another 14. I got 64. I got 64 for this one. How? How is it doing this? Okay, at least we got all the strings. And at least these are the same. Wait, oh my god. Guys, this is really good. This is really good. We got 250. 250. Oh my god. Actually got it. We actually got it. Oh my god. Okay, but we got a little more. We considered a little more strings than they did, I think. Somehow. I don't know how. Don't ask me how. Oh my god, we're so close to doing this correctly. Okay. Question. What if we don't fill it with 1s? What if we just switch the symbol? Right? What if we just switch the symbol? And then we see what happens. Alright, we just switch the symbol. Alright. Maybe it will just automatically flip everything. And then that'll be cool. So yeah. So we don't change the tape. Oh, jeez, guys, I'm getting like hiccups or something. I don't know what I'm doing. I'm like burping, half the burp. Like, ugh. Alright. Oh, look at that. Oh, come on. We didn't get all the strings. We didn't get them all, but what? I mean, that makes sense. It makes sense. You know, we flipped the symbols, but we didn't flip the tape. So it turned out weird. Okay, so let's look at the thingies here. So here we got 3, 3, 5, 5, 4, 4, 30. Let's see if we considered, we did, right? Yeah, we considered the same amount. Here we did 8, 3, 8, 8, 6, 8. Right, ends in 608. And here we got the same. Okay, we got the same amount. Here we got something. I don't know if we got, I don't know. I don't actually know what to do with this information. I don't really know what to do. Because if I don't put ones, there's going to be a bunch of zeros. Okay, I have a question. What if we put ones for this one and zeros for this one? Like, what if we do that? What happens then? Does this generate the correct table? And also, why did it go quicker? That's weird. Why did it go quicker? I think it was the tape. Like, some of them didn't halt, or like some of them halted quicker than they should have. I don't know. I don't know. But we're gonna continue. I have no clue. I mean, it went a little quicker. It was basically the same. Basically the same amount. The same amount of stuff. Alright, let's continue. Let's continue the journey here into this paper of us trying to calculate. Okay, well, we got all the strings now, which is good. Here we have 18. Here we have 14. That is very, very close. Very, very close. Not quite exactly good enough. Close enough. Oh my god, we're so close, bro. We're so close. Okay, how about up here? What about the right here? Here they're still the same. Alright, which is good. Okay. This is weird because these are all different now. I guess maybe they were still all different, but oh, these are all different as well. These are all different. Length 3 strings. My length 3 strings are all different. I don't know if that's a thing here. Let's see, 0, 0, 0. I got 0.02. Which they did not. They got a different number. So yeah, there's a problem. There's a problem. I don't know which you know, I don't really know. We got closer though. I mean, this is 14. This is 18. We're just 4 off, right, from being the same. And we still have all the strings, right, which is pretty good, you know. And we're kind of on the order of magnitude, right, of the same thingies, same probabilities. These are 0.10. which we kind of got almost. This is almost 0.1. These two are almost 0.1. This is almost also 0.1. We're kind of like approximating, you know. We're approximating. In the 4 or the 3, let's do the 3. So here we got 0, 0, 0, 0. I got almost 0.01. It's 0.01 greater, almost 0. You know, whatever. It's pretty close. 0, 0, 1. You know, I got a pretty good 0, 1, 0 though. This one 0.00. It's still very close. It's like on the order of magnitude. These are all like on the order of magnitude the same, and I'm able to still generate all of them, which is a good sign. So I really don't know what I did wrong. I don't really know what I did wrong. I mean, I don't know. I don't know. What about this? Length 5, 0, 0, 0. Let's look at that one. What's this? 4 zeros and a 9. I got 4 zeros and an 8. Come on. Come on. It's so close. It is so close. I don't know what they did. This number, again, I keep getting like a number multiple of whatever these people, whatever they were getting. So let's do this divided by their number. And it's 2. Again, what is happening here? I am considering more machines than they are. Like, what is happening here? Like, what is happening here? Maybe it's this. Maybe it's this. Do I ever use total ever again in the calculation? I don't think I do. No, I don't really. I use total strings though. Oh my god. Okay, I do use total strings. But the thing is though, in the frequency table, I mean, they all start at 0, right? They all start at 0. And I just don't get it. What is happening here? How do they do this? What are they doing? I don't know. Okay, because right here, because if I do this, right? If I do this to get the same, you know, 15 million instead of 2 times 15 million, I guess I said I do this instead. I'd add total strings. I increment the total strings once instead of twice, so that should give me their number. Alright, I hope it does. At least, I don't know. I'm guessing it will. Oh my god. Alright. This is gonna take a second. This is why I want to use that freaking library to speed things up. Okay, look at this. What is going on here? What is going on here? We get a pretty close number. Like, it's just close. It's not exactly. Right, it's not exactly. Come on, I missed the 1. Give me the 1. Oh my god. My gosh. Minus this number. Alright. So we got this. I am considering too many machines. Is that what I'm doing? Am I considering too many of them? Huh. Okay, I think what I'm doing wrong is I am considering the Turing machines. Oh my god, I knew this would happen. I actually knew it. I actually knew it. Okay, so the problem, right, the problem is that I have too many machines. Considering just slightly too many machines. My hypothesis, right, is this. Okay. This. Okay, so let's plug in that function. I'm going to plug in that function into my calculator. Right, and I'm going to... No, that didn't work. What did I do? Is end transitions? No, this isn't right. How many oh my god. Here it is again. My numbers do not deviate from the the internet. What is happening? What are they talking about? Okay, so in here the problem though is I think I'm considering too many transitions because I think on their paper they do not consider the halting transition, but I do consider the halting transition, and by that I mean in here in the Turing triples, right? We consider all of the transitions. So I'm gonna have to do something. I'm gonna do another test. Okay, I don't like this. I don't like this. Okay, I just don't like it. Let's do something. Let's read the code. Alright, let's read the code. Okay, and let's do a little thinking. Okay, a little bit of thinking. And the problemo here is that our transition table, we are considering in our calculation of the frequencies the halting states in the transition table. Like, we're iterating through all the halting possible transitions. So like on here, for example, so if I had two states, right? How many transitions is that? 4, right? Apparently, because we got 2 0, 2 1. I mean 1 0, 1 1, and this is 4 of them. But my algorithm considers these two as well. Considers these two. So I think what's happening is we're considering this many, too many of them. And this is the triple, right? This is the triple. So what I'm going to do is do the calculation real quick. So each transition has a state that it could be in, right? A state. And this is to the power of something. 2n, let's say, I think it is. And each of these, yeah, so we got this times 4, I think. So just, what is it? Is it this? I don't know. Let's just plug that into the calculator. So let me plug in 4x to the power of 2x, and I'm gonna look looky look on the calculator, and I think it's not working. For 3, I got different thing. I think it's supposed to be something else. I don't know. What is it? This is the states. This has 2 possibilities. This has 2 possibilities. So it's n times 2 times 2, right? And how many transitions do we have? We have one. We have n times 2 transitions. So yeah, that's that. I don't know why this didn't work in my calculator. I mean, they say they have this many. Here they say they have this many. And I got a slightly different number. Alright. Let's continue real quick. And I gotta do something. Here, I gotta do something. I have to not consider the 0 state or something for some reason. And that kind of makes sense because it's like I'm not gonna consider that many transitions. I'm not gonna consider that many transition triples. Oh wait, hold up guys. What the hell? Never mind. So yeah, I'm not gonna consider that many transitions. Cause like if I had 2 states, it would be this. I could have n. Here I could have 2. Here I could have 2. So this is times 4. So this is 4n. This is 4n. Right, 4n. 4n. So 4n to the power of 2n. Right. So this is 2 states. 0, 1, 2. I think I'm not supposed to consider these. So maybe this is supposed to be minus 2. Because we're... Yeah, 2n to the power of 2n minus 2. Which is actually... something. Alright, so let's go check that out. Kind of... This is, kind of... Right? This is still not right all the way. Because they got 20,000. Right? I got 20,736, which is this number. And for the next one, I still got this number. So I don't know where they are getting that number from. I have to do more reading. And let's see if they what they do with that, because that's kind of weird. Alright, let's revert the code back to normal. In here, where I don't do strings thing here, I do it here because frequencies don't match up if I don't do that. Alright. Let's continue here. They gotta give me some type of formula. Alright. Some type of formula. I don't think... Yeah, I don't really know. So they do... Oh, look at this. They give the actual code. Huh. Beautiful. They give the actual code. So here they're considering stuff. They do M transition table. Their code is a lot cleaner, to be honest. I should probably... I'm eventually gonna have to rewrite my code maybe to include more stuff. Okay, but this is kind of weird. They do a, what is this, 2D? They have like 4 directions. They got 4 directions. Yeah, this is, yeah, yeah, so their thing kind of is different. Yeah, they do 2-dimensional. Cool. Okay. Look at that, they do something there. So number of machines. Number of machines. They do a different. They do an estimation. Here they do some. 2, 1, 4, 6. That is not a thing. That is not a thing. That is not a thing. Halting and runtime. Wait, what? Can only halt at non-random times. I don't know what that means. Producing random machines. Oh. Cool. Okay, well that kind of makes sense. Guys, I gotta go to the bathroom. I'll be right back. Okay. Whoops. Okay, we're back. We're back again. So they have code. I want to see here. Whoa. Hmm. So I have to go to the appendix. Oh my god, they provided source code. They provided source code! What is GMP? It's a library. I think I've been coding on hard mode. Yeah, look at that. This is for this is precision. This is for precision. Okay. Arbitrary precision. Zen 5, why? It died. It had a discoded region. Unfortunately, it died in the same way. Oh my god. So it overheats if you use it too much. Oh my god. Guys, I'm gonna probably have to rewrite all the code or something. Okay. Or something. Because this code is crazy. This code is crazy. It's not that crazy, but it's pretty kind of crazy. I don't really want arbitrary precision. I'm okay with like lower precision, but you know, I don't know. Look at this. Look at it. Okay, so you can put in the numbers. You know, that's so handy. That is actually so handy. So they put here, so you can put the number of states, the number of symbols, which I was thinking of doing. This is the maximum runtime, and first last are integers representing machines in the reduced enumeration. Yeah. 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 Okay, so to return a table with the output strings of all halting and non-halting codes. What does it return? I want to see an example. An example. Oh, look at that. Wait, let's see here. I have 500 something lines and they have 200 something lines. You know, they have some comments too, but yeah. So this is cool. So what do they do though with... Wait, what? Is that it? Is that it? Don't they... Do they have code for... Oh my god, do they have code for, what is this? No halting transition? Oh. -2. Okay. So, what is the result? So they just output all the frequencies, and if it doesn't halt, they just add that. Cool. Well, let's take a look at this. I'm bored. Let's just take a look at this. What is this? So there's numbers, mediation analysis performed with scaled data as computed from the data set and with our other stuff. So what is it? What does this even mean? Visual cognition. What do they do? So they look at images. Oh lordy. That's pretty cool. What? What does conspiracy theories have to do with this? Algorithmic probability. Oh my god. That's actually crazy. What? Wait, what? Conspiracist ideation and the rejection of randomness comes from the correlation found between endorsement of conspiracy theories and paranormal beliefs. Such beliefs have repeatedly been found to be associated with the misperception of random noise as ordered patterns. That's actually funny. Wow, I mean that's true. That sounds plausible to me. Jeez, that's kind of funny though. I didn't know, talks of randomness would do something like this. It would like they'll talk. This seems so random. Oh my god, they did experiments on it? No way. So they act. Yo, this is all cool. This is actually really cool. So it's all about cognition. That's pretty cool. Wow. Contrary to our initial prediction, it was not found to be associated with low prior for randomness, even when randomness was opposed to deliberate and malevolent intentions. So what? That the nothing happens by accident heuristic, if it applies at all, would involve high levels of information processing and cognitive integration rather than a core low level and quasi-sensory disposition. Cool. That is cool. So, climate change skepticism is an analogous phenomenon. It is unrelated to scientific literacy, but is strongly dependent on more general ideological cultural factors. One cannot take the expression nothing happens by accident at face value as an explanation for conspiracist ideation. So there's more to it than just nothing happens by accident. How did they do this? So there's an experiment. So you have to judge sequences composed of the two symbols X and O. They may correspond to heads or tails or odd digits, or to a series of successes or failures. So it could be represented by this much, it could be represented by that. Some of these sequences are created using a real fair coin, which means that they are random. Other sequences, however, correspond to non-random processes that they may come from computer calculations or from sport performances. Okay. For each sequence, your task is to decide whether it was truly random or it could be the outcome of a non-random process. You would do this by selecting the response that seems more appropriate. Please answer as fast and accurately as possible. That is cool. That is cool. So what do they do? So that's their ability to discern randomness. And then in here it says, an unrelated project aimed at validating a French translation of questionnaire of political opinions. They filled out a 15-item generic conspiracy belief scale, which captures generic conspiracy ideation without alluding to specific conspiracies. That is interesting. That is interesting. The next participants read two scenarios describing situations of potential conspiracies, one interpersonal and the other political, and were asked to rate the perceived probability of conspiracy in these situations. These four conspiracy scales were counterbalanced in four orders, and there is some demographic information. 1 second, guys. Alright, I'm back. So, let's see. Oh my god, what is this? So subjective randomness and true randomness. Was it contrasted with an unspecified deterministic process? I don't know what this means, to be honest. Do not know what this means. What is this? Subjective randomness? True randomness? So there is somehow a link between subjective randomness. But what about the... let's see. Subjective randomness was not significantly correlated with any measures of belief in conspiracy theory. In the mean, subjective randomness of strings was linked to their true randomness. What? Oh yeah, I'm not really too sure about this. I mean, this is funny, bro. This is an online experiment. Oh, they freely took part in an experiment. Yes. So... I don't know, bros. There's a bunch of random stuff in here. So... algorithmic complexity of short strings. Yeah. So they're talking about memory. So being able to compress information is related to intelligence? What? What? Um, where do they do the ACSS? Where do they do that? The block conditional method. So I want to go up a little bit. Is there a thing? So right here they say they estimate it using the methods described. Okay. So yeah, they use probably this. Algorithmic machine learning. Oh my god. It's changing every day. It's changing every day. So this is a thing. Bro, okay. So I'm almost done. I'm almost done with the coding theorem method. To be honest, I think what I have right now is probably usable. It's probably usable. Yeah. It's probably usable in the sense that it has frequencies that are on the order of magnitude that are the same as as what's it called, as in the paper. So that's good. That's good news. Here though, I do want to see. So they'd have zeros and then the blank symbol thing. So that's cool. So I do the frequency thing. Okay, so my next thing that I want to do is go forward with this. I want to go forward with this, and probably not today, but I'm pretty happy for this, what we have right now. You know what? Let's actually try something. Let's try something. Let's do something. Let's look at the coding theorem. What is it? Bro, they even calculate D5. Jesus, terabytes? Oh my god. This is crazy. They had a bunch of CPUs. This is crazy. Oh my god. That's kind of crazy. That's kind of crazy. Jesus. Um. How do we use our information here? How do we use our information? What is this? Alright. That's not real. Uh, How do they get the complexity? Alright, so they do this. Whoops. So actually, just kidding, they say the coding theorem. The coding theorem. Oh my god. Okay, so where's the coding theorem? It's here somewhere, right? The limits of stuff. Alright, here we go. Here we go. So here's where they calculate the thing. And here, what do? They just do the negative log of the frequency of the string. Oh, those are probability values. Okay. Okay, let's do something. Let's get the probability of this string, I guess. Let's plug this into the calculator, my calculator. So I'll put 0.1234879. I got 13.47. And this one, for example, is the same thing, but it has a 2 here, kind of slightly more complex. Yeah. Okay, so I'm pretty satisfied with this, and that I'm satisfied, and I think we can use it. Right? I think we can use it. The only problemo is there is no problemo. Yeah, alright, we're gonna do this. We are gonna do this. So right here, what am I, where did I just put that variable? It's right here. Yeah, okay, so I'm gonna put max, and output length, and we are going to use said thing before we do this. So max, we're gonna set that, and then at the end I'm going to print largest length string found, and then I'm going to put that. Yeah, okay. Alright. Oh my god, bro. Jesus. Okay. Okay. Yeah. So I'm gonna let that run. I'm just gonna make sure this works. The last thing that I added. And then I'm just gonna call it. I'm just gonna call it there. Or play ratio. I'll see what happens. Let's see here. Alright. Yeah, we found 7. We found 7 of them. That's a good. Largest like string found. How many strings have frequencies greater than 0? I want to print. I'll put here non-zero strings in total. Okay, so I'll do that. Here, this is the very end, so I'll put how many strings? Here, I'll put yeah. Okay. So here I got strings. Greater than max. Max length. Strings longer than max string length. So I put this strings longer, number strings longer, found longer than. Let's do that again. Actually, let's put where does this go? Come on. Let's put this at 7, for example. That'll include some strings that are too long to fit in the thing. Ow. Ouch. That was weird. Alright, whatever. So yeah. Let's see what that gives us. I really want to split this up, bro. Using MPI. MPIC. I could very much do it. This is just a lot of code, so that's a problem. That could be a lot of things that could go wrong, I guess, when you try to parallelize code. Yeah. It can be that hard, really. Turing machines, the only thing that has to be parallelized and, like, chunked up is the search for Turing machines. That's what I want to do. So I think I would make a function that, like, I don't know, lets you choose Turing machines from a certain range, and then yeah, and yeah. So I found 114 non-zero strings, apparently. That's not technically correct, is it? Is it? Kind of weird, because we only go up to 6. And yeah, we didn't even consider. We didn't consider Right here, I think. I need to consider this. Max num thing. Max string length is 7. Number of strings greater than max or greater than, so it can equal 7, right? Is that what that equal? Is that what that means? Yeah, it can equal 7. Right, so I think I have to do something here. So this can include 7, so I don't know why. Because it said 0 strings thingy, but it didn't include the 7, up to 7. I think I'm supposed to do this. Well, actually, not really. Not really. I'm supposed to do this. Include the last size. Because I said so. We want to get all the information that we can get. All the information. Okay, yeah. So, yeah, what I want to do is use my laptop as well as my computer here to make a cluster, and then, you know, after I do that, you know, after I do that, I can do stuff. So here we found the stuff. Right, it does include length 7 strings. I'm gonna need a way. I'm probably gonna put this into a CSV somewhere, like make yeah, I don't know, I'm gonna make a CSV or something where I can, you know, look for a string and then do something with it. Like I'll put this, a big CSV basically, and it'd just be like this probably, like frequency. I don't know. I could do that. I can include that. So like the frequency and you know, stuff like that. Also, I don't know. I don't know. Okay, so this is good. All right, this is good. What I want to do for my next step is I want to make a calculator thing where it will print the frequency for or like it'll print the algorithmic complexity estimate that it has for a string. You know what's weird? This is weird. The strings have higher complexity than themselves. Yeah, the strings have higher complexity. That's what it said on the paper too. So, yeah. Yeah, interesting. I don't know. Interesting. I always wanted to do something where like we approximated this thing, and you know, I just leave a computer running, and it'll be like just approximating. Like it'll just continue, like it'll never stop, like trying to, I don't know, find the difference between all the Turing machines. I don't know, bro. I don't know. I don't know. Oh my god. So they brute force it. That's literally what this is. Like you brute force the motherfucking I don't know, bro. Mother flipping. What if we do resource bounded complexity? Right. Like instead of Kolmogorov complexity. So you supply the limits, and then you get your strings that are produced, and then you get your estimation of the complexity using the coding theorem. I don't know if the coding theorem, because the coding theorem works for the string, probability of a string. That's what that is. You approximate M. That's what that is. My goodness. My goodness. Why was that so difficult? Why was that so difficult to figure out? Where is the universal distribution? Where is the universal distribution? I think it's here. Yeah. Yeah. Okay. This is something. So the algorithmic probability of a thing is you sum up all the programs, and then you get the ones that, like, yeah, I don't know, probability. You approximate it. I don't know, the probability. That's what we're doing. We're just checking all the Turing machines, and then we plug it into here to get the something majigger, and then it's going to be like added, you know, by a constant. It'll be a difference. Majiggy. Alright, because look, we can look here. Actually, no, let's go here. And compression of 1 to the n. Okay, well, okay. So I don't know what they do with this constant, to be honest. I don't know what they do with that constant. Okay, how about this? So you search for the string, right? So you search for the string, And that's what I wanted to do kind of with this one, where you would find the complexity just by searching through all the Turing machines and then looking for the ones that give you a string that you want. And the complexity will be the size of encoding that Turing machine in bits. And that's up to the person who encodes that Turing machine. You can encode it using a certain number of bits, log n. There's like an upper bound according to how many states you have. You can encode a different, a different thing, but yeah. How about this? How about it? So you get the specific Turing machine, and then I don't know, bro. With that Turing machine, you encode it, and then you could calculate that. It's gonna be approximate. That's what that squiggly line means, right? Squiggly line, I'm not sure. I think that means proportional or something. I don't really know what that means. Yeah, we can just hmm. Wait. Huh. So they just used 500, and they used the thing here. Okay, so we ran this many random Turing machines up to 5,000 steps. Only 50 of them halted after 500. Wow, only 50. We don't include the ones that halt in one step, or that we know won't halt before generating them. Okay, that's cool. So, yeah, that's pretty cool. So, given the unknown values for the busy beaver, we do not know after how many steps they would eventually halt if they ever do, according to the following analysis. Our election of a runtime of 500 steps provides a good estimation. Okay, that's cool. So it drops exponentially. And our experiments are closer to the theoretical behavior. Yeah. Mm-hmm. Six to the times 10 to the power of negative 173. Wow. Okay, so there's a string that has a probability of 1 point. Okay, let me just plug that into the calculator and see the coding theorem thingy. So times 10 to the negative 9, and it's 29 complexity. So this is far below the point where it could possibly compare the results. The less probable still a string as in observed probability of this much. Huh. Okay. This is much higher than our previous estimates. Is that true? It produced 99,000 different. Wow. That's crazy. So up to 40 something, 49 bits. Oh my goodness. Okay. So we have the probability and so they're observed solid and the theoretical dotted. I don't even know about this. The repetition has a lower probability. Is not surprising. $3.13. Okay, so they do stuff. They do stuff here. Bayesian. What the heck? Okay. Okay. So they're comparing these. So these are the probabilities. They're very aligned, basically. That's cool. What is this? I don't even know what this is. I don't know what rank means, but So that's interesting. So the single bit is 0.25 in complexity, so it's 2, which is cool. Complexity value is greater than length. 212 of the strings have greater string lengths than program size values. The first string to have a smaller program size value. Then the string length is this. Oh. God damn. Oh my goodness, alright. This is crazy. So this string is length 14, but has 37 complexity. So, what? So it has a higher complexity than its own length, which is kind of interesting. Robustness, how sensitive is it to N? Yeah, I don't know. Oh, so they calculate values. So they calculate C actually to be around like 5. It's like between 4 and, well, here it was like 2 almost. Five bits is the greatest difference. What the? Okay. So what is this? These are 10 entries, but for a fixed input, I don't even know about that. Distribution of the complexity values according to the number of instructions used for 5. So if they used all the instructions, they were more complex. So just by halting and knowing the number of instructions that it used, you can estimate the complexity. So that's pretty cool. That is pretty cool. So if you used 3 instructions, it was pretty low complexity. And yeah. That is pretty cool, actually. Okay, so instructions used in string lengths. So you can generate more higher string lengths with this. I don't know what logical depth means, but yeah. Machines which generate each string using the minimum number of instructions also has minimum runtime. Okay. That's cool. Goddamn, they used all different types of stuff. Hmm. God damn. What is all this, bro? Images. Oh my god, bro. Multi-dimensional complexity? What? 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 Okay, I kind of want to try this. God damn, I do eventually want to implement this. Not gonna lie. Alright, so I think I'm good for today. For later episodes of coding this thing, I think I'm gonna have to simplify the code quite a bit. Maybe remove some functions I don't use, or keep them. I don't really care. But keeping this all in one file, it was nice. It was easy to do this. It was pretty easy to do this, but you know, it's getting unwieldy. All right, it's getting unwieldy. So I think I'm gonna have to change it up a little bit. You know, change it up, make a header file or two, or three or four, and make a proper build script. Maybe, I don't know. Maybe turn this into like a library. I have no clue. Maybe I'll keep it all in one file, which is a little insane, but I'll see what happens. I don't know. I'll see what happens. Maybe I'll increase like the number of symbols as well. I don't know. I have no clue. I have no clue. Okay, I have no clue. This is serving my purposes so far. So yeah. So yeah. We got that. I got that. Alright. I'll see you guys in the next video. Peace out.